IABAC. Our speaker for today is Mr. Anirban Mukherjee, and the topic for today is Generative Adversarial Networks in Artificial Intelligence. Let me give you a brief intro about our speaker for today. Anirban's interests lie in the fields of AI and data science. Currently, he's pursuing his master's in data science from IIT, Bangalore, and he's done his BTech in computer science and engineering from UEM, Kolkata. He's worked on projects in domains including natural language processing, computer vision, time series analysis, edge computing, and he also enjoys doing research while making open source contribution and he's intent on exploring more in AI. Over to you, Anirban.
Yes, good afternoon, everyone. I'm audible?
Yes, you are.
Okay. So hello, everyone. I'm seeing many of you have joined. Thank you very much for joining. So today's topic is, as Rama said, it's Generative Adversarial Networks, or GANs in short. And so the main discussion about GAN is needed because nowadays the task of creating like synthetic images and synthetic data in general, that is increasing very much, and the quality of the data which is created, that has also been improving a lot. So that's why I thought of choosing this topic, and we will be like shortly discussing about like some of the like existing architectures, existing applications, and just first we try to understand what GANs are and how they like work and what they are and what's like why are they suddenly so good at doing what they are doing. So that's all about. So this is what we'll be discussing. We'll be talking about generative models in general, like so like first we have to understand like what's the generative part of the generative adversarial networks. That's something we'll discuss. Then we'll be talking about GANs. We'll be getting into the framework and the architecture of GAN, and then we'll be looking at some of the existing applications of GANs. Okay, so far so good, I'm hoping. So just a quick question while I'm discussing is that like I'm hoping that all of you are sort of aware with types of model like classifier models, image classifier, face recognition, or maybe the dog cat classifier models. If you are aware, maybe you could like type on the chat if you're aware of that kind of model. So those are the very basic kinds of models which we see most of the times. Like classification models, what they do is the model takes in an image as an input, and then the model does some computation, and with that they're throwing an output. So let's say we want to build a model which classifies, let's say, whether the picture is of a face or not, right? So we'll give the picture of a face, and it will give an output of 1 if it's a face, or near to 1 if it's a face, and near to 0 if it's not of a face. So that is what a typical classification model does. That's what we mostly know, right? Now the question is, let's say we have a very good classifier model, a very good face classifier. Okay, so it is able to classify with high accuracy, and that means that it has some understanding of what a face looks like, because that's how it is making that decision that yes, this is the picture of a face. But the question is, if I ask it to create an image of the face, can it do that? And the answer is no. Right? It's only good at classifying the faces. It's not able to like, create or like generate any synthetic kind of like face, given how good it is at classifying. So that is where we come to the context of generative models. Okay, and it's not just about images, also it's about any kind of data. So what generative models try to do is that they try to learn how the data was generated. So they're not just interested in learning about how to give the label to the input. So label is the output for a supervised task. So they're also interested in learning how the labels and the data, most importantly, how the data is distributed. So they're trying to learn how the data was generated by learning the probability distribution of the data itself, right? So the main difference between a discriminative model, which is not a generative model, and the generative model is that a discriminative model learns just about how to make the label, And the generative model learns how the data is generated, the distribution of the data. And so there's a quote by Richard Feynman that says, like, what I cannot create, I do not understand. So if you think of it in context of generative models, so the generative models are trying to learn the distribution so that they are able to create, right? And that's how they're understanding. So once a generative model is able to create something, it's learning the data distribution, it's able to create the data. And with that information also, they can even classify the data. Okay. So some common examples of these generative models that exist, they are the naive-based classifier model, the VAE, which stands for variational autoencoder, and GAN, which we will be soon discussing about. So is it clear? Okay. So we have understood the main intention of generative models. So it's to learn the data, learn the distribution of the data. So GANs also fall in the same category. So a GAN, or a generative adversarial network, is a framework for teaching a deep learning model to capture the training data's distribution. Like I said, it's trying to understand how the data is distributed so that new data from the same distribution can be generated. So its main task is to generate new data. That is the main task of a GAN model. Okay. So given the task, now we have to understand how it does that. Okay. So before getting into the model itself and like understanding how it does that, let me tell you a story. Let's say there is a forger, like a fraud person who is able to forge fake currency bills. Okay, he's able to like create fake money, right? Currencies. So he has been creating these fake currencies for a long time. Okay, and now we have a detective. Okay, detective who's very good at classifying that whether it's a fake image of a currency or a real image. Okay, he's very good at it. So when the forger is creating the images, at first the images are not very realistic. It looks very fake, and the detective is easily able to say this is a fake image. I can say this is fake because I know what a real currency looks like, and I know that these are the reasons why this is not a real image. The fonts are wrong, the numbers are wrong. So he knows that the image is a fake. Now the forger learns this, he gets punished maybe. So the next time, again, when he creates the currency, he's again not creating very realistic, but he's slightly improving. Because of the feedback he got from the detective before, he knows what changes he has to make in order to make the data a bit more realistic. So he's doing those changes. But now also again, when he's creating that fake note, again the detective is saying this is also fake. It's somewhat realistic, but it's still a fake, I can say, because the font size is not matching with the real currency font size. So this keeps happening. And what happens over and over with time, the forger becomes better and better at creating the fake currency. He's creating more realistic currency, right? So this is like, just keep this story, because this is a very good story to understand how a GAN is actually trained and how it works. So I hope you have understood what I've said till now. So now let's understand what GAN is doing. So in a GAN, there are essentially two models. Okay, one is the generator model. So from the name, you can guess that this model is generated, right? So taking the example of the fake currency, this can be thought of as a forger, right? He's creating like synthetic data, right? And the discriminator. Discriminator is the detective, right? So the discriminator's task is to identify whether the data generated is real or fake, right? And these two models are trained together in a zero-sum adversarial game. So this is where the term adversarial is coming, because the generator and the discriminator, they are constantly fighting with each other. They want to like win over the other person. So in a zero-sum game, it's one person is winning, one person is losing, right? So that's the main concept, that the generator and the discriminator are trained together in a zero-sum adversarial game. Okay. So that this is about the architecture, and just talking about these two things. So as we have discussed, the target of the discriminator is to accurately classify between real and fake data, while the target of the generator is to generate samples which are good enough to fool the discriminator. So I hope the narrative of the forger and the detective is now fitting in place. And so is it clear to everyone? If if you want, you can feedback if it's clear, if you have any doubt regarding this part. Like, this is the very basic introduction. Now, just to get to the model side of the things, so if we look at how the generator is creating, so first the generator is taking some noise, we can say. It's basically, it can be thought of as a vector, and it's called a latent variable. So I'm not getting into the details about that thing, but think of it as some sort of information that doesn't make sense to us, but it's a random noise. Okay. So the generator is taking this random noise as its input, and with that, it is generating new samples. Okay. So these samples, as we can, generator wants to generate samples of the images of faces. So the generator creates these generated images, right? So we call this G of Z. Why? Because random noise was Z. So it's the generator, we call it G. So it's G of Z. Okay. It can be thought of as a function. So now we have this generated set of images. The generator has done its work. But is it realistic? Till now, the answer is no, because it hasn't learned anything, right? Now, along with these, we have a set of real images. Okay. So we call this X. So these are real images of faces. Okay. And looking at this, we can say that which one is real and which one is generated, right? But now the task is, how do we train the generator? So like I said, for improving the performance of the generator, there has to be a discriminator in the whole architecture, right? In the framework. So now we have the discriminator. And okay, before the discriminator, we have to understand that the real images, we are saying that they are having a label of 1. And the generated image, we are saying they're having a label of 0. Okay. So it's a very simple way to understand that here we do not have to manually label anything, right? Like in many data science tasks, in many machine learning kind of tasks, labeling is a huge problem, right? It's costly, it takes time. So here we do not have to do that. Whenever it's created by the generator, we are automating the process. Whenever the generator is creating, we are saying it's y equals to 0. Whenever we have the real set of data set, we're saying it's y equals to 1. So with this label and with these images, what do? We feed it to the discriminator. Okay. Now the discriminator, think of it as just a classifier. It is a classifier. It is able to differentiate between what is real and what is fake. That is what is generated, right? So the discriminator is the detective, like I said before. And what the discriminator does is gives an output of how realistic the image is. So it lies in the range of 0 to 1. Okay. So this is the overall framework of the GAN, as we can see. And this generator and the discriminator, these are basically neural networks. So that's why we call them generative adversarial networks. Okay. So till now, is it clear? Any question, any doubt if we have? And so whatever I'm telling you till now, that now this is the framework. Now the question is, we have to learn this, right? Now, like, how do we train this? Now, for training any machine learning models, we need some kind of a loss function, or we call it a value function. Okay. So it's basically a function which the machine learning model optimizes. That's how the machine basically learns. So if let's say we are trying to make the machine learn how to classify faces and pictures which are not faces, so the loss tells us how much of fake the face is of. And we reduce the loss. The more we reduce the loss, the more we optimize the loss, the better the model gets. So now the question is, what is the loss function which we can use here? And this part is a little mathematical, but we don't have to get into the details of how we've come to this equation. I've just highlighted the key parts of this equation. And so we have this value function which we have to optimize. And so we have the first term here, this, and in here you can see there is a term of d of x. Now the d of x is basically the discriminator's output of real images. So when the detective looks at a real currency, what will he say? He will say it's a real image. So he'll say it's an output of 1. So this part has an output of 1. The d of x has an output of 1. And when he looks at the other term, which is d of g of z, now the g of z, remember, it was a generated image. So whenever the discriminator looks at the generated image, he says it has to be an output of 0. That's the ideal case. That's what, like, for the discriminator, that should be the case. He should say that whatever is the real image, it's an output of 1. Whatever is generated image, it's an output of 0. And so since d of g of z is 0, so we say that 1 minus d of g of z is 1. Just 1 minus that, right? So now this is the value function. Now comes the interesting part. How do we optimize it? Right? Usually we minimize the loss, but here what do we do? Here, the discriminator wants to maximize this, Because like I said, that d of x should be 1, d of g of z should be 0, or 1 minus that part should be 1. So the discriminator wants to maximize this value. For the discriminator, that will be good, because that means the discriminator is giving the right outputs, right? But here's the thing. The generator wants to do just the reverse of that. So the generator wants to minimize the chances of the discriminator giving the right output. Okay. So you can see this part, you can see it's the min-max. So this is what we call a minimax scheme, where one party is trying to maximize something, the other party is trying to minimize something. So here is the adversary that is happening in this whole framework, right? So this is how we use the value function. And so this is just about the loss function. Those who are more interested in implementing that, maybe this will be useful. And just to understand what happens here, if we look at this figure, it says that the dotted is, we can see here, right? The dotted, I'll annotate it. So the dotted part, here, this one is the real data distribution. Okay. And this green one is the generated data distribution. And the blue is the classifier. So we are not concerned that much with the classifier, the discriminator. We are more concerned with how realistic images can be made. So initially, we can see they are far apart, right? They're not overlapping in some sense. But with time, we will see that the classifier will, the discriminator will be improving. But what the most important thing is that these distributions are overlapping, right? So if you compare these two images, if you compare, look at here, this one I made, and if you look at this one, so they are much more nearer. And here, which is an ideal scenario, they have overlapped. So at this stage, we say that the generator has very accurately learned the distribution of the real data. Okay. Now this is an ideal case. This computationally, this might not happen, but this is what we intend to happen. Okay, this is how we are making the model learn. And when this happens, so we can see it's written that the D outputs a probability of 0.5 everywhere. So why 0.5? So if you go to the detective and say, hey, what's the chance of this image being real? And if the detective is saying 50-50, so there's a 50% chance. So that means he doesn't know, he's just leaving it to chance, right? So that means the discriminator has been fooled completely, and the generator has succeeded in being able to create synthetic data. So this is the overall information that I had to give, like, about GANs that I wanted to say. And this is the very basic kind of GAN architecture. After this, we have very different kinds of GANs, which I won't be getting into the details of it. But the main differences which exist, they exist in the way we define the networks, right? Maybe we use, instead of a traditional perceptron model, we use a convolutional neural network, maybe, or so that's some kind of modification in the network part. There may also be the modification in the value function, which we saw. Maybe we wanted to learn something else. So there we have to modify the value function. Maybe there is some other kind of input other than the random, the latent variable, which we saw. So in that case, we are trying to, we are optimizing with a different value function, right? So overall, these are the parts of the GAN model, and the main intention is that this figure, like where the generator is able to fool the discriminator and able to create realistic kind of data. Okay. So that's about GAN. Any questions anyone has? Any slide you want me to like iterate again? Or any doubts you have, you feel free to ask. I'm looking at the chat here. And if the chat is coming from YouTube, I'm not looking at the YouTube. So maybe I can have the chat here also. If Ram, maybe you could check it out. Okay. Okay. So moving on, the next thing which I want to discuss is, let me clear the annotations. So the next thing I want to talk about is some of the applications of GANs. Okay. Now here, like, based on what application it is, we have different kinds of architectures, but I won't be getting into the architectures mostly. I'll be mostly talking about the use cases, right? The industries where it is used, and like how it could be utilized, how like generating synthetic data could be utilized for someone's benefit, like maybe for reducing cost, or like automating certain processes, or even improving certain AI applications themselves, which we will be looking at right now. Okay. So anyone has any questions? If no, I shall continue then.
Go ahead.
Okay. So, so the most popular kind of application which we see, that is generating synthetic images, right? So you might ask, why do you want to like generate synthetic images? Like, what's the like, how is it? What's the utility behind that? So there are many use cases. First of all, if we are able to generate synthetic images, realistic synthetic images, then we can use them for many cases where we are training some machine learning models and we maybe do not have enough data set, right? So in those cases, we might be like we have some model of what a face looks like, but we want to create more variations in that, in how the face will be looking like, right? So in that case, we might be interested in creating new images from the given distribution, right? So whenever we need to learn the distribution, the GAN will be useful. It is learning the distribution, and we are able to like sample from that distribution, and we're able to create new images, right? So that is one use case. Other than that, if you look at this image, so the creative people might be interested in creating images for like animations, right? So there also, if like these images we are seeing, let's say these are mostly of anime. The anime is a particular type of like drawing. If someone's trying to draw the picture of an anime, so it has a particular type that exists, right? And it cannot be, it's difficult to explicitly say what it is like. So it's difficult to automate it like that. But if we have a GAN that is able to learn what like anime in general looks like, then we can utilize that learning of the model to like create different samples. These samples, as we can see here, these are created by a GAN, and that is sort of like saves money, saves time for when we are talking about an industry that's wanting to create like some characters for some animated movies or something, right? So these are some of the use cases of generating synthetic images. And so these were just generating synthetic images from like just creating something new. Other than that, we have this application, which I find very interesting, which is taking from a blueprint to a finished architecture. So if you look at this figure, so this is essentially taking as an input the picture of, it's taking an input a picture of a blueprint of some kind of architecture. Let's say we want to create a building, and it is taking that blueprint, and with using a GAN, it is able to create the whole picture of a building, right? And that's amazing if you think about it, that like the machine has some understanding of what buildings look like, and also it has the capability of taking in blueprints and converting those into the final buildings that we are talking about, right? So this is a very useful application in many cases, in engineering, you can say, in designing. And it's not just about buildings, but any kind of structures, maybe for interior design or anything. Many applications are available nowadays also, where we see that you can sketch something and the output comes up. So those are always utilizing some sort of GAN kind of architecture in most cases. Okay. Other than that, we have like this kind of thing where we want to generate training sets, and this is very similar to the one which I told you. But like the intention here is to generate training sets for machine learning models, right? So we know in all the data science models they require huge amount of training sets, and let's say for some tasks like self-driving cars and all, they need this kind of training set where they're having an idea of how the traffic looks like, and maybe we want to create some particular type of a situation uh, of the car, of the vehicles and all. But it's costly to like draw it completely from scratch, right? Or editing it in Photoshop, it's costly. So using a GAN, we can just feed in some maps, as we can see in the image here, and that takes in those maps and converts those into this kind of finished output. So this is similar to the blueprint to the finished structures example, but the use case is slightly different. And that this is also possible because of GAN kinds of architectures. Another kind of application is super resolution, where the GAN takes in an image with a low resolution, and it is able to expand to something which is of a high resolution. Now, there are traditional methods to do this as well, but using a GAN, the quality of it looks more realistic. The quality can be improved very much. And also, this I actually forgot to mention. If you look at the image at the top right of the slide, so this was actually this paper has an example of how realistic the images have gone from time to time. Like in 2014, this was the picture of a synthetic image, but we can see in the year 2017, this face, like anyone wouldn't be able to say whether it's a picture of a real face or a fake image, right? So yeah, the quality of GAN has improved a lot over the years, and it's still improving. Another application, we have photo in painting, right? So if we see here, so in this image, the left side of the image, so a chunk of the image has been taken out, like it's white. And the GAN, since the GAN knows what an animal may be looking like, so GAN is able to generate the part of the image that was taken out, and it's able to generate the full image completely, right? So this is also useful. This could be useful in some examples you see where in many mobile apps we want to erase some. Let's say you have a picture of a floor and there's a shoe on it, and you want to erase the shoe. So we sort of erase the part of the image, but maybe with a GAN it can generate what the floor would look like. Right? So there's some use cases I'm talking about that can be thought of, and that's very successfully done with using a GAN of any kind. So those were some of the image kinds of tasks. Mostly they were concerned with images, but other than images, we have these examples also where we are going from text to image. So this is very, I find it very interesting if you look at it. So if you're feeding some sort of text to a GAN, right? So like if you look here, so sorry. So if the description of the bird is given, right? It's a white bird with some black on its head and wings and has a long orange beak. So it is just taking the text, it knows how to go from the text to the image. So just with that, it is able to create a realistic image given the text. This you can guess whenever you want to create some images, this kind of application, like this kind of an architecture could be very useful, right? Going from text to image. It's completely two different domains we can go to. Also, GANs are able to, it's not just limited to images, but it's also able to create, generate videos. And although they are similar, but in videos, you can guess that the time is a factor, right? So let's say a ball is at one point and at the second frame, it's at another point. So using a GAN, you want to generate further frames, like where will the ball be in the future? So that kind of, the generation process can be done using a GAN. And with that, we can actually generate videos. Right, and that of course it's looking very realistic because of the GAN's quality, GAN's ability to generate like very good quality images. Okay, I see some questions here. Okay,
We
okay,
did this at the last.
okay, I'll attend the question at the end. If I might come back to any of the slides if you have any doubt regarding the slide, and I'll explain those. Okay. So generating videos we did. Now we have another kind of application, which is basically it's called style transfer. And with that, I'll play the video, and I hope it will play. I hope you can see it. So see, here as an input, we gave the image of we gave the video of a horse, and it was able to produce the video of a zebra, and it is just able to convert the style of the horse to that of the zebra, right? So this is something which we call style transfer. And so a GAN can be trained to do style transfer like this. And so that could be very useful if you think of use cases. And style transfer is not just about videos, it's also used in images also, like we saw in the blueprint to the output and all, but here it extends to videos as well, right? So this could be one application. So till now, what we discussed, they were mostly related to images and videos and that kind of thing. But other than that, there are other use cases also for GANs, like for example, where we want to like build a simulation, right? In many applications. So I don't know how many of you are aware of reinforcement learning as the part of machine learning, but like any reinforcement learning, basically we're training some agent. You can think of it as a robot in a simulation, right? In a world of its own. So the robot is interacting in the world, and with that interaction, it is able to learn. So you can guess that it becomes very important to build a realistic simulation, because the more real the simulation is, the better the robot is at learning, and the better it will be its performance in the real world. So not taking for the robot example, here I have a paper which takes the example, it's the use case of a recommender system. So what happens here is that the reinforcement learning system is trying to learn how to recommend like some content, right? Maybe recommend videos or movies to the user. And so for one challenge that can happen is maybe the let's say you're watching Netflix, right? Now you want to generate more and more use cases where you clicked one series and after that you clicked another series, right? So that kind of data, it might not be available completely, but we might have some amount of data for that. So using a GAN, we can like we can create more like synthetic data set. And so with that itself acts as a simulation. So like given a recommendation, you see how the simulator is responding, whether it's clicking on that recommendation or not, right? So it's a basic recommendation system. So where GANs can play the role of a simulator, right? So that is one use case of GAN. And another use case I found very interesting is it's used in physics experiments. Right? So this paper, like they use like high energy in for high energy particle system experiments. So the building the simulation and doing simulation experiments, they're very costly. Like they're like extremely costly. So using a GAN, if they're able to build a simulation that they have done in this paper, the simulations reduce the cost. They say that they have reduced the cost of millions of dollars have been saved. And so that kind of simulation is also useful. So you can see it's not just about computer science and images and audio, but it also extends to like physics kind of application, like other domain, it's a completely different domain. And like there also GANs are able to like efficiently learn about how a system is, how the simulation could be like, and able to create a realistic kind of uh, synthetic data that is very useful for the use case, right? So these are some of the applications that I wanted to discuss, and with this I come to the end of my presentation. Uh, that's about me, and okay, now I'll quickly look at some of the questions that are existing. So okay, how to use GAN for missing data set? Okay, so whenever we say missing data set, we like let's say we have a data set of face images, right? So I'm giving a real example that has been discussed in one place. So let's say I have a data set of face images, okay, and I see the face images. The faces belong to a particular color, let's say, okay, belong to a particular race, maybe. But we know that when we want to train a classifier, we must ensure that the data set should be diverse, right? In other words, there should not be any kind of bias in the data set, right? So in that cases, what we can do is if we are able to build a GAN that is able to generate faces, and that GAN with the generating part, we can somehow say that we wanted to generate faces of some different kind of color, right? And that control can be done in the latent variable part. So if I quickly go back to the slide where we looked at the latent variable part, because I didn't discuss it too much, but it's actually a very important thing in the whole architecture. So this latent variable, if we are able to manipulate, we are able to change what the generated images look like, right? So there might be a case where if we are changing one value in the latent vector, we see that the color of the face is changing. Maybe there is again one value in the vector which if we're changing, we are seeing that the pose of the face is changing, right? And this kind of helps us to give some control over over how to like make some changes to give the output. And with that kind of thing, we can create more variations in the data set that we have, right? This is a use case I told you, but in general, the like for using for like how GANs are used for filling in the gaps of missing data set is very much like that. Since it has learned the distribution, we can create more samples, right? And we can take care of the like oversampling and undersampling aspects that exist, right? And things like images. So like for oversampling, there are other techniques also like SMOT and like synthetic minority oversampling and all, but those exist for structured kind of data. But for unstructured data, like as far as I know, GAN type of models they're mostly used for filling in those gaps, right? So okay, so there was a question by Jiffy, if I'm pronouncing it correctly. How can we scale GANs beyond image synthesis? So these are some of the use cases as I showed. I hope you've got the answer. If not, you can ask me if any particular kind of domain or use case you're talking about. But how can we scale GAN beyond image synthesis? So that's the thing. Like it's not just about it. We can generate videos also. We can generate simulations also. Simulations for RL system. Simulations for physics experiment. And so whenever we want to create samples from distributions, I feel that GANs can be very useful in those use cases. Okay. So next is a question of Stephanie. How should we evaluate GANs and when should we use them? Okay. So the evaluation part till now, as far as I know, it has been done just by looking at it, right? Because like, of course, one way you're saying that how good the discriminator is performing, that is one way it is evaluating the generative part. but how is the overall output that we are getting? So that like for face images example, we can look at the image and we can say that it's a realistic kind of images. Also, there have been like some applications. So basically, there have been some use cases of GANs where since you are able to generate synthetic images, so they have been used for malicious intent as well. So there have been certain some applications which were able to detect images and videos which are generated by GANs, right? So those are able to distinguish between what is GAN generated and what is not GAN generated. But overall, we can say that yes, by looking at the image. Also, if you are looking at if you're talking from the training perspective, how should we evaluate GANs? There is no as such metric that I know of. Other than maybe the accuracy of the discriminator, of course, it tells you if it's close to 0.5 for all the examples, we can say that yes, this is like for a given architecture, this is the best it can do. So that is one way to evaluate that whether my GAN is performing very nicely or not. So I hope that answers your question. And when should we use them? So as I told you, like whenever we want to learn the distribution of some data set and we want to sample from the distribution, we want to generate synthetic data from that. So that is the main place where we are using GANs. Okay. Mariana has a question. What is the relationship between GANs and adversarial examples? I'm not sure I understand this question because like what do you mean by adversarial examples? If you could just say, because like so the part in the GAN where it is the generator is trying to do something while the discriminator is trying to do something else. So that is where we say that is they're adversary to each other. That is the adversarial part of the GAN framework, right? So that's the thing. So GAN uses this kind of adversarial training method in order to like make the generator learn in a better way.
Hey, Anirban, can you just actually emphasize a little bit more, like, one of those things you said that, if you don't have a data set or um, can you give us more examples of what could possibly be adversarial examples in terms of whether it's a generator or the discriminator?
Yes. Okay. So I'll then go back to the slide where I talk about that adversarial part basically. So about adversarial examples, I don't know what to say, but where the adversary is coming into the play, this is like I can explain from here only that like adversary means they're competing against each other, right? So now since like I said that this part where the d of x, this means that the discriminator's output when it takes the real image. Okay. So from this last slide, we can see that the real image here is x and the generated image here is the g of z. Just keeping this in mind. So the the discriminator is taking the real image and it wants to give an output of 1. Okay. So the output should be close to 1. Ideally, it should be 1, but it's close to 1. And what should be the discriminator output when it's taking when it's taking g of z? So d of g of z should be close to 0 because it's a generated image, right? So this should be ideally close to 0. And because this is close to 0, we're saying 1 minus this thing is close to 1. So now is the main part where the adversarial training is happening, is that this whole thing, whatever I told you that the d of x should be 1, the d of g. So I was talking in terms of the discriminator. So for the discriminator, all these values should be maximized, right? This should be 1, this should be 1, and this should be maximized. So this max d, which I've written here, I just annotate it. So this max of d, which I've written here, so this is saying to maximize this value function. And the generator wants to do the reverse of that. So because of that, the generator wants to minimize this thing, right? So the generator wants to minimize this whole value function. And so by minimizing this value function, what is it doing? By minimizing this, it is actually minimizing the chances of the discriminator giving right output. The discriminator wants to give right output and like beat the generator in producing fake images. And the generator wants to defeat the discriminator by minimizing the chances of discriminator giving the right output, right? So this is where the adversary is happening. One is trying to fool someone and one is trying to identify, like, detect someone, right? So this is the adversarial part of GAN. And I hope I was able to answer. Mariana, if it's clear, uh, then just you could like say, or you can ask if you have any further doubts. Okay. So next is what are the trade-offs between GANs and other generative models? Okay. So I'm not getting too much into the other generative models, but just to give you a brief idea of how the main differences between just the three generative models I told you about. I told you about the knife-based model, the VA, which is the variational autoencoder, and of course the GAN, which I talked about. Uh, okay. Yeah. So the knife-based classifier basically it's basically the first generative model which most people usually learn, and so using that, what happens? Usually what happens when we are doing a discriminative model, we are saying that given the input, what is the label, what is the output, right? But what happens in a knife-based classifier? We are saying that given the output, what does the data look like? Okay. So given the class, we want to understand what the data looks like. So in that way, we are learning a joint probability distribution between the data and the output, and then we are using the Bayes theorem, which is I'm not getting in the details of that, but it basically uses the information of a likelihood that what is given the class, what is the data. It uses this likelihood, and then it uses two other things, one which we call as the prior knowledge, and one which we call the evidence. So using these information, the knife based classifier uses to classify that what is the possible output for the model being of for the input being of a particular class. So that is something which we call the posterior. Okay. So basically the Bayes theorem is about like finding out the posterior using a likelihood, a prior, and an evidence. So I'm not getting the details of that, but you can check out that the knife based classifier. It's a very simple kind of simple kind of generative. And so the next model which exists is the VAE, which is the variation autoencoder. It's actually it's a very useful kind of model. And before GANs, like they were highly used to sort of in these kind of tasks also, where we want to take samples from that. The main thing about VAE is that what VAE does, they take in some sort of data through a network. Oh, by the way, the VAE is a neural network model. So this is, you can think of one difference between the knife base and the VAE and GAN. So VAE and GANs are neural network models. So the VAE takes in the data, it compresses it to a very low dimensional vector. In fact, this vector is the same concept which we call the latent variable. So not getting into the details, but so a VAE takes an input, let's say of an input image, compresses into a very small size vector, and then regenerates the image. Okay. And so we can say, what is the point of regenerating the same image by going through a compression kind of thing? The answer is what exists in the compressed part of the model is the main thing which we're interested in. The latent variable that exists there, that tells us that what is the main thing of an image that I need to know so that I can generate the image, right? So if I annotate it, Ram, just could you tell me how much time I have? So I don't know how much I'll answer.
We have 10 more minutes. You can proceed, Anirban.
Okay.
We have a couple of questions in the chat as well, apart from the question and answers.
Okay.
We have a couple of questions there as well, if you can take it.
Oh, I haven't seen that. Okay, fine. Okay, I won't get into too much detail, but essentially, so that's how a VAE works. It works by compressing an image or I'm taking an image as an example, and then reproducing that image. So when it has learned that latent vector, so using this latent vector, it is able to generate new samples. So we can make small tweaks in these latent vectors, and then we are able to generate new samples. Well, what I told you, this is of an autoencoder. So variation autoencoder is slightly different from it, a slight modification over it, but like the basic concept is of an autoencoder. And so yeah, this is the kind of thing, and the loss it uses is it uses some kind of a mean square error kind of loss. So I'm just talking about the differences mostly, and so that is what the VAE and the AE uses. But whereas the GAN uses the loss which we saw. In fact, one thing I'd like to say that for the generator, we can say that the discriminator is sort of a loss function. If you think about it, that the discriminator is learning the generator is learning how good it is performing from the discriminator, right? So that is why we say that, like, we can say that discriminator is sort of like the loss function for the generator. So yeah, I hope that has answered, like, briefly answered your question. Okay.
Yeah, we have a couple of questions in the chat.
Okay, chat.
The last three. One from is GAN used in Mona Lisa?
Wait, I can't see the question. Where is it?
It's in the chat.
Yes, I'm open. One second. Is it recording of this? I don't see the Mona. Okay, was GAN used in the Mona Lisa? I don't know what exactly, because Mona Lisa was painted. But if you're asking if you can create a realistic kind of looking, let's say you want to create a Mona Lisa kind of painting using a GAN, so that kind of things have been done where the model has taken, like, inputs from a particular kind of painter, and they have tried to, like, generate similar kinds of paintings, right? So it's like not, it's highly unlikely it will produce another Mona Lisa, but most of the times it uses some kind of, because it knows the distribution of what the painter draws, like we can look at some painting and we can say, oh, this looks like the painting of this particular painter. So how do we do that? Because we have some understanding of what the painter's paintings are like, that such that even if the painting is different, but the style of it and the feel of it is the same. So GANs have been able to, like, do that. So that is one place where you can say that, yes, this kind of applications exist where they've used to generate images from similar kinds of painters, right? Okay. So other question?
It's from Hassan.
Yes, Mohammed Hassan. Okay. So how GAN, SR GAN, and ESR? Okay. So I'm not getting the details of it. There are architectural differences in there. So SR GAN, it's like super resolution GAN, and enhanced super resolution GANs, how they have, like, how they're related and evolved. So I'm not getting into the details of it, but overall the thing is, like, taking an image, they're trying to recreate that kind of image, and, like, the differences are mostly like using some kind of different kind of variation of the GAN, or maybe some difference in the loss which exists in one kind of GAN which doesn't exist in the other kind of GAN. So using that kind of modifications, with time they have evolved, and even now, like, that's how we have a much more high resolution images that exist. Like, initially the GAN which you're saying, if you're saying about a very traditional GAN, so they use a perception model. So later they've started using a convolutional network kind of model, which we call as a DC GAN, and yeah, so those are the things. So I think I posted the links of the paper. I think it was of SR GAN, so maybe you can check out about the details of it. But yeah, I'm not covering that now. Okay, so the question is, okay, Ahmad wants a summary. So you want the, I can share obviously I'll share the slides, and the video will also be available on YouTube, if I'm not wrong, Ram. So maybe you can check it out later. Okay. So in the question panel, is there any other question? No, I don't see any other question here. So anything else anyone wants to add? Any feedback or? Okay.
I guess we have had our list of questions answered. Hey, Anirban, thank you so much for taking your time out, and it's been quite enlightening, to know all your research work, as well as, like, your work on these adversarial networks. And thank you everyone for joining in. We'll keep you posted on the upcoming series of our webinar series, and thank you everyone. Have a nice day and have a nice weekend. Thank you, Anirban, again.
Thank you. Bye, everyone.
Hey, Hasid, thank you so